Okay, so last time, on Tuesday, we discussed complex analytic signals, the complex analytic signal representation of an optical field. So today we will once again revisit some of the essential mathematical concepts from stochastic processes that will be of relevance to optical coherence. So this will be the second installment of discussion on stochastic processes, and next week we will go into the investigation of interference and temporal coherence. Okay, so today we will discuss temporal correlations, so by the way, those who are online, so how much time do you have? So can we go until 3:45 or whatever? Do you have any other, so can we discuss for 45 minutes to an hour? So how does the schedule look like?
So we can have till 4 o'clock if you are for you.
Yeah, sure. Okay, great. Okay, so you can see the board, right? Is it clear?
Yes, sir, it is clear.
Okay. So what is the first thing? So once again we will revisit the concept of stationarity. So this is something that we discussed a few weeks back when we introduced stochastic processes. So we'll once again revisit this concept, but today we will discuss stationarity only in the temporal domain. So stationarity will also show up a little later when we discuss spatial coherence, but today we'll confine our discussion on stationarity to temporal coherence. So when is a random process said to be stationary? So a random process is said to be stationary when all the correlation functions are independent of the origin of time, right? So now let us consider a generic correlation function of order 2n. So what does this mean? We are just going to write down the nth order correlation function. Okay, this is an nth order correlation function, right? So when is this said to be stationary? So if this nth order correlation function is stationary if this one equals In other words, you just shift the origin of time, the correlation function should not change. If this condition is satisfied, then the random optical field or the random process is stationary. Is this clear? Any question? So formally speaking, you can always introduce correlation function to any order. However, experimentally, it's very difficult to determine the correlation functions to all orders, right? And this is because primarily due to the fact that the probability of detecting multiple photons or simultaneous photon events decreases exponentially, or it decreases drastically. So it's extremely difficult to measure higher order correlations experimentally. So that's why in all the investigations in optics, we pretty much confine ourselves to second order correlations. Okay. So in most physical scenarios, we confine ourselves to second order correlations, and we treat the process to be White-Sun stationary. So can I clean the left side of the board?
Yes, sir.
Yeah. By the way, those attending online, have you ever had a course on stochastic processes?
No, sir.
What about some basic probability theory?
Yes, sir. That has been done.
That yeah, okay. So you're familiar with some basic probability theory, calculating correlations, expectation values, so on and so forth, right?
Yes, sir.
Okay. So is it clear so far? Are you able to?
Yes, sir.
The ideas are clear?
Yes, sir.
Yeah. Feel free to stop me if something is not clear. Okay. So of stationarity. So this is something that we discussed a few weeks back. So what is White-Sun stationarity? Mean is independent of time. So if you calculate the mean of the random of a White-Sun stationary random process, it will be independent of time. Okay? And the intensity, so which means so what does it tell you? If it is stationary, then the mean should not depend on the origin of time. So whatever mean you calculate at t will be the same as what you calculate at t plus tau. But t is arbitrary. You can pick your t. So if you set t to be 0, then whatever is the mean of this random process at the initial time should remain so forever as time evolves. So that's why for a White-Sun stationary process, the mean is independent of time. Right? So is intensity. So intensity which we denote by I of RT is defined but that should be same as t plus tau and this is nothing but the intensity at time t equals 0. So that again, so I should write this as R0. So is this clear? For a Whiteson stationary process, the intensity is also independent of time. So whatever intensity you measure at the initial time will remain so as the system evolves as time evolves, right? So what about cross correlation function? So can I clean this part of the board, the right side?
Yes, sir.
Okay, let me just write this. Can you see the bottom part of the board? If I write at the bottom of the board, can you see it? Or is it not clear?
This is visible, sir.
With the button you can read it, right?
It's visible.
Okay, okay.
Yes, it's readable.
Okay. Okay. So what about cross correlation function? So how do you define cross correlation function? So cross correlation function is basically tells you how the field is correlated at two different space-time points. So you are basically we are trying to calculate what is the correlation between the field at points r1 t1 and r2 t2, right? And that is defined as so. For a Whiteson stationary process, I'm just trying to subtract t1 and add t here, and you will see why we are doing it this way. Now, cancel this one. Now, this t2 minus t1 is basically tau, the difference between the two instants of time. So this basically becomes t plus tau, or you can also set t to be 0, in which case so the correlation function simply depends only on the time difference. It does not depend on the absolute values of the times. It does not depend on what t1 and t2 are actually. It only depends on the difference between t2 and t1. And this is what you will get for a Whiteson stationary process. This is not always true. It is not that the cross correlation function always depends only on the time difference. Only for a stationary random process is this property satisfied. Okay. Okay, so let me clean this part of the board. So which means what we find is the following: if the process is stationary in the White sense, then the mean becomes independent of the origin of time, and the cross correlation function or the two-time correlation. And why is it called? This is also called the two-time correlation. Why? It depends on two time arguments. The two-time correlation or the cross correlation function depends only on the difference of the two time arguments, t2 minus t1. It does not depend on the absolute values of t2 and t1. Right? Is this clear? But this is true only for a stationary random process.
Yes, sir.
Okay, so the cross correlation function has some properties. So sometimes this is also denoted by gamma of tau, because it does not depend on t1 and t2, and since we are only interested in studying the temporal correlations for simplicity, simplicity of notation, we suppress the spatial coordinates. So sometimes we just write the correlation, the cross correlation function, we write it as gamma of tau. Okay. So when the delay is 0, gamma 0 is always greater than or equal to 0. This means and it is 0 if there is no field. What does it mean? It is just that if you turn off the field, the correlation vanishes because there is nothing. There is no field present for you to calculate the correlation. And and what is gamma at 0, tau equals 0? If you just set R1 equals R2, what do you get? It is basically V conjugate of R0 times V of R0, which is nothing but the intensity of the field, right? And intensity should always be positive. The intensity of light is never negative, okay? And the intensity becomes 0 when there is no light, right? So that's what this property tells you. So the absolute value of gamma of tau is always less than or equal to it's less than or equal to the value of the correlation at tau equals 0. Right? So it tells you that the degree of correlation now, it's important to keep in mind that this property does not tell you that gamma of tau will always decrease. No, it's not that gamma of tau should either monotonically decrease or increase. Over an interval of time for a finite delay, gamma of tau can increase or decrease depending on how small or how big the delay is. But all this property tells you is that no matter what, the absolute value of gamma of tau cannot exceed its value at tau equals 0. So the correlation is always maximum at 0 delay. Okay, that's what it tells you. The third important property is Okay. This is hermeticity condition. This ensures that V of RT So let us see how to prove this one. So gamma of tau is in this case we are simply setting R1 equals R2 for simplicity, right? Now replace tau by minus tau. So what do you get? Gamma of minus tau is basically right. Now let t minus tau be denoted by t prime. This means t equals t prime plus tau, right? So let me clean the left side of the board. So now it becomes R t prime plus tau times V of R t prime, right? Now I'm just going to exchange the swap the order because these are random functions, and t prime can be replaced by t because t prime is only a dummy variable. So what do we get? This is same as V conjugate of R of t times V of R t plus tau whole conjugate, which is nothing but gamma conjugate okay. This is the hermeticity condition. This is how you prove it, right? Any questions so far? So is the proof clear? Is the reasoning clear?
Yes, sir. Yes, sir, it's clear.
Okay. By the way, have you had a course on optics in your grad school or undergraduate program?
No, sir.
No. So you are a graduate student, right, or an undergrad?
No, we are engineering in EC.
Oh, okay. Oh, engineering students. Okay. Doing your BTech?
Yes, sir.
Okay.
BTech completed, right?
Oh, okay. No, but okay. But you have some exposure to basic optics, correct? Interference, some basic ideas. So please let me know if
Means actually I'm working in wireless sensor, so interference, correlation, these things we have idea.
Oh, you have idea. Okay. So you're able to follow the reasoning, right?
Yes, sir. Yes, sir.
Okay. Thank you. Okay. So I suppose can I clean the board, both sides?
To continue.
Yeah. Okay, so next we will discuss spectral properties of time domain random processes. So sometimes it becomes it's a lot more convenient to study the temporal correlations in the frequency space. So why is this? Why do I say this? So we consider this random process V of RT. So V of RT is basically the optical field, a random optical field, which is which is basically a random process due to the statistical fluctuations. Now, it's not always guaranteed that the Fourier transform of V of R sub R comma T will exist. So there are occasions where the Fourier transform of V of RT wouldn't exist. Okay, and this is because V of RT is not always absolutely integrable. So we won't be going into the mathematical, the subtle mathematical aspects. We'll just state this fact. If you are interested, Wiener has studied this in detail, so you can consult any mathematics book. But we'll just state the fact here. So it's not always absolutely integrable, which means the requirement, if a function is absolutely integrable, then this requirement has to be satisfied. Integral mod V of RT dt should always be less than infinity, and this is not satisfied. So you cannot always say that if you are given a random function V, that you cannot claim that its Fourier transform always exists. It may not exist if the function is not absolutely integrable. Nevertheless, the correlation functions are square integrable. So we will use this particular fact, the fact that the correlation functions are square integrable, to derive the spectrum. So for the purpose of our discussion, we will assume that we'll assume that the Fourier transform of V of RT exists. In other words, we assume that we implicitly assume that we are considering only those random processes which are square integrable. Okay, so which means if you are given a random field V of RT, then it can be represented by its Fourier transform. Okay, so right here we are only taking the Fourier transform in a symbolic sense, in a mathematical sense. So we are not assigning any physical meaning to the Fourier transform. So we will ascribe a physical meaning only when we calculate the correlation function. So right now treat this as a mere mathematical operation, that if you are given a function, you are writing that in terms of its Fourier transform. Okay. So likewise, V of R omega can be written in terms of V of RT. Okay, and as you know, these two form a Fourier transform pair. Okay, so is this clear? Any questions so far? Okay. So now let us calculate the cross correlation function. By the way, if my handwriting gets smaller, please let me know. So how do we calculate the cross correlation function? So we are just going to substitute for V conjugate of R1 T1 and V of R2 T2 in terms of their respective Fourier transform. Okay? So is this step clear? This particular step. So I hope you can see what has been done. We have simply written down for V conjugate of R1 T1 and V of R2 T2 in terms of their Fourier transforms, their respective Fourier transforms. Is this step clear? Any question or any?
No question, sir.
Oh, this is just still done. Okay. Now, the randomness is present only in these two functions, not in these exponents, right? So the expectation value can be taken inside the integral. Right? So, okay, I'm going to clean this part of the board. Now that equation can be written as, this is nothing but gamma of R1 T1 R2 T2 which by definition oh, I'm sorry, made a mistake, typo. Can be written as now we are introducing a function w. We will define what w is in a moment. where this W by is called defined as a cross spectral okay. It's a definition. So we define a quantity called the cross spectral density function. I'm sorry, this one again. Made a mistake. So W of R1 omega 1 R2 omega 2 is basically the expectation value of V conjugate R1 omega 1 times V of R2 omega 2. Okay. So So let us write down these two quantities in one place. So W and gamma form a Fourier transform pair. So this is something that you need to have in your notes and box these two results. This is called, gamma is called function, W is called so gamma is in the time domain and omega W is in the frequency domain. Okay, so let me clean this part of the board. So suppose I can clean the left side of the board, right?
You can clean.
Yeah.
Even full board also you can.
No, I want to just retain the contents on the right side for the time being. Now, for R1, if R1 and R2 are the same, say those two equations, these equations written as so because R1 and R2 are the same, we are dropping the coordinate R. So we are just going to suppress that particular coordinate in the argument of gamma. Okay, so just gamma of T1 T2 equals W of omega 1 omega 2 likewise this one, these two together form what is known as the generalized Wiener-Khinchin theorem. So let me clean the right side of the board. So this basically relates the 2-point correlation function to the 2-point cross spectral density function. Again, why is it called 2-point correlation? Because the correlation function has two time arguments T1, T2. That's why it's called 2-point correlation function. Likewise, the cross spectral density W has two frequency arguments omega 1, omega 2. That's why it's called 2-point cross spectral density function. Okay. In principle, you can always define higher order correlation functions, but we will confine ourselves only to second order correlations in this course. Okay, so since you come from the ECE background, electrical electronics engineering background, so have you seen this one? I'm sure at some point in time, did you ever have any course on random signals or whatever? Signal analysis, random signals?
So the random signal analysis covered, but this theorem specifically I am seeing first time.
Okay, you're seeing for the first time this particular theorem, Wiener-Khinchin theorem.
Yes.
Okay. But you have seen the correlation functions and spectral density functions, right?
Yes, sir. Yes, sir.
Okay.
That helps.
Okay, okay, okay. Okay. So any questions so far?
Sir, what is basic significance of calculating this 2-point correlation at same distance, with same position? Because now we are making R1 equals to R2 equals to R.
No, no, you.
So we are seeing cross relation across time.
Yeah. So.
Same position.
Yeah. So your right now our focus is on calculating the temporal coherence, the temporal correlations, right? So we are right now not interested in the spatial variation. Of course, you can also calculate the spatial correlation. Nothing stops you from having R1, R2 different. You can certainly have and calculate, but our focus is to see how the optical field is correlated at two different instants of time.
Okay.
Okay. So right now we are simply ignoring the spatial variation.
Okay.
Okay. But we'll come to that a little later, maybe next week or week after next, when we discuss spatial coherence, where we will calculate how the field is correlated at two different points in space.
Okay, sir.
So right now our focus is to understand temporal coherence, how the field is correlated in time. Okay, so now let me clean. So can I clean the board?
Yes, sir, you can clean the board.
Okay, thank you. Okay, we can define something called degree of temporal coherence. And this is defined as now this gamma of T1 is nothing but intensity. When you calculate the correlation at the same time, you basically get the intensity of the field. So this I of T1, intensity at time T1 and intensity at time T2. So this is called the complex degree of temporal coherence. So why complex? Because gamma can be a complex quantity. Now, if you just consider the magnitude of this little gamma, it always takes a value between 0 and 1. So 1 corresponds to perfect correlation, between the fields T1 and T2, and if it is 0, it means that there is no correlation, no coherence. It's and any value between 0 and 1 simply tells you that the field is partially coherent. Okay. Now, the fact that the absolute value of little gamma, the degree of coherence, temporal coherence, should always take a value between 0 and 1 can be proven using the Cauchy-Schwarz inequality. So, probably I'll try to erase the left side of the board. So, suppose I can erase the left side of, or maybe can I clean the whole board?
You can clean, sir.
Okay. So I hope you have noted down whatever you want to, right? So I can clean the board. Okay. Now, recall the Cauchy-Schwarz inequality. You need to so for any two complex functions xi of t and eta of t, the following inequality holds for their averages. So basically, once again, xi and e. Okay, this is the Cauchy-Schwarz inequality. So, just going to apply that to the 2-point correlation function. So, we are going to prove for the most general case where R1 T1 and R2 T2 are different. So, from the Cauchy-Schwarz inequality, this has to be less than so this by definition this is nothing but you are calculating this at the same time. So what does it tell you? So once again, we are suppressing the spatial coordinates for simplicity. So take the square root. And of course, this should always be greater than 0. So, and this is basically and why should it always be greater than 0? Because in the denominator you have the intensity of the field at 2 times T1 and T2 that has to be positive, and this modulus value cannot be less than 0. So the lower bound is always 0. Okay, that's how you prove it. So this is something that you might have seen, right? The Cauchy-Schwarz in engineering. In any of your engineering mathematics courses, have you come across the Cauchy-Schwarz inequality?
Yes, sir, this was there. This was there.
Okay.
Yes.
Okay, so you're familiar with this result, right? Okay. So let me clean the board. So if gamma is 1, then it means there's perfect coherence. So this tells us that field at T2 perfectly predictable. T1. In other words, there is a perfect, the wave maintains a constant phase relationship over the time delay tau, T2 minus T1. Okay? That's what this condition tells you. When gamma is 1, there is perfect coherence. If gamma is 0, then there is incoherence. There is no coherence at all, which means no correlation between that. So the phase relationship is completely random. So I hope you can read what I've written at the bottom of the board, right? So my handwriting became a bit messy at the bottom. I hope you can still read it. Or do you want me to write on top again?
Sir, what is the last line?
Oh, okay. So I'll write it again. Let me clean the, okay. If gamma is 0, then, which means the field is incoherent. There is no coherence. So this tells you no correlation between the two. Okay. The phase relationship is completely random. Is this clear now?
It's clear.
Okay, let me erase this one. Now, if gamma is between 0 and 1, if the degree of coherence is between greater than 0 but less than 1, then this corresponds to partial coherence. This is what we expect in the real world. So most of the realistic sources are partially coherent. So this tells you that the field has some degree of correlation, but it's not perfectly predictable. Okay, I hope you can read this one, right? Is this clear, or the last sentence?
Yes, sir, it is clear.
Okay. Let us see. I think we will stop here because the next one, it will take a while, so probably we'll do it next week on Tuesday, coming Tuesday.
Okay, sir.
So any question on today's lecture?
Sir, this T1 minus T2, that tau, that coherence time,
That's a delay.
that
No, that's not the coherence time. That's not the coherence time. T tau is T2 minus T1 is just a delay.
No, but it will have coherence for that much time only.
No. So you can so we can calculate. The thing is this. So how much the delay has to be less than the coherence time. If you so yes, but tau in itself is not the coherence time. So the question is, how far apart in time can you measure the correlation will depend on the coherence time of the source. So we'll we will discuss that probably next week, like as how we can define the coherence time in terms of the correlation functions. But when you want to study correlations, the fields will remain correlated only if your delay is within the coherence time. You're right. But the tau that you saw in the expression for gamma, the cross correlation function, that tau in it by itself is not the coherence time. It's simply the delay, t2 minus t1. So in principle, your t2 minus t1 can be anything. It can take any value. You can have it as large as you want. But it's just that if the delay exceeds the coherence time, you won't be able to make measurements of correlations.
Okay, sir.
Yeah, so this tau is very general. It just corresponds to the delay, the difference between the two instants, t2 minus t1.
Okay, sir.
Okay, so any other questions? So